Okay. So after I developed the SETI model as a control theory problem and was able to solve it completely, many attempts have been made to extend that model by groups that are associated with me and people who are not associated with me. And I'm going to cover two such extensions, and they are both in the book. And then a few more extensions that are still going on. One of them is the 3-echelon model. I will only spend maybe 5 minutes on it, just to tell you what's going on at the moment. So when there are two duopolists in a mature product category where the total sales are distributed between the two firms. So what's going on here is that there's a market share, which we take to be 1 without loss of generality. And somehow the arrows don't work. Do the arrows work? Or did you?
You have to do it from top one time and then it works.
Okay, I am trying to do it. Oh, you go this way and then it works? No, it doesn't work. I think you have a control, I don't have it.
Give it to you, Professor. It says to reset the S control.
Well, it's not working. It's not working either way.
Can you click on the arrow on top?
I am doing it. I am clicking on the arrow. No, it's not working for some reason. I don't know why.
Is your mouse turned on?
Mouse is good. It's got light. It's I see the arrow.
Let me remove control and then give you control back. Let me see if that works. Okay, try now.
No, for some reason, neither the mouse nor the wheel works. I don't understand what's going on.
Does the mouse work somewhere else besides this screen?
I'm trying.
Okay, let me close these. Stop sharing and then I'll share again.
Yeah, the mouse is working everywhere.
Okay. Okay, try now, Professor.
Oh, what's going on? No, nothing is working. Thirdly, stop control, request control, request control. Request. Okay, I requested the control. No, the mouse doesn't work on this at all, but it works on the rest of the place. I'm open to open the mails. Yeah, it works everywhere. Something is a problem. Should I go to the slides on my end? Okay, give me back the slides. Otherwise, I'm going to go and share screen or something. Kushali, are you
trying to share the slides from your screen, or do you want me to play them again?
Try one more time, and then otherwise I will.
Okay, try now, Professor.
No, no, no. Let me try my side.
Okay.
Okay, I'm now with mine. Can we screen share here? Screen share. Screen. Can you see that now? Can you see the slides, everyone?
Yes, we can see that.
You can see my slides?
Yes, Professor.
Okay, and this, my mouse
Yes.
works.
Yes, we can see it.
Okay, so we have a duopoly market, and we have a firm one and firm two, and they compete for market share. So what happens is let xt denote the market share of firm one at time t. That's a random process now. And 1 minus xt is the market share of the firm two. And we assume U1T and U2T, we denote by them to be advertising effort rates for firms 1 and 2, respectively, at time T. We let Ri denote the effectiveness of the parameter for ith firm. Pi I is the sales margin, rho I is the discount rate, and Ci bigger than 0 is the cost parameter of the cost of advertising effort. And we assume the advertising effort is convex. Cost is convex, which means the diminishing marginal effectiveness of advertising. You can either have a dollar value in the objective function and then have a square root of that into the dynamics, or we can have the effort in the dynamics and the dollar value of of to be square. So they're equivalent. The delta be the churn parameter. Churn means going sales go from one to the other by many things that are going on in the economy. And ZT be the standard Brownian motion, and sigma x is the diffusion coefficient. We already talked about that in section 12.3. Then, as in 12.3, the Sethi model was extended by Prasad and Sethi. This is what I'm doing now. Prasad and Sethi 2004 paper is what we are covering right now. And so we have R1 U1 times square root of 1 minus X. This is for the X guy, that's firm 1. And the firm 1 is losing the share of the market by forgetting and attrition and whatever. And the other guy is taking the market from firm 1 because the other guy is also advertising. And he's advertising to the people who are buying firm 1's product. So see, his advertising is acting on 1 minus X. These are the people buying firm 2's product. This advertising is telling the firm 2 guys, hey, buy my product. On the other hand, the firm 2 is telling my customers, hey, buy my product. And so he's taking something away from mine. And then there's a churn. Churn means I something is coming from the other one, but then of course other one has the same situation. Okay. And there is a Brownian motion which makes the thing stochastic. As in the original Sethi model, we have an objective function for each firm, but this is the extension. These two are the extension by Prasad and Sethi. Okay. There was another person who wrote a paper where they did not have this, but they had this term. It was my former postdoc named Sorger. He was the first one to extend this to a game model. And then we have a definition of the value function. This is the initial market share of the first firm. But that's, remember, we only need one state variable because the other firm just takes 1 minus x. There's another model which is different than this model. Um, um, okay, so yeah, so we have two value functions, and they play Nash game. So we do the Hamilton-Jacobi-Bellman equation like we do usually, but of course there are different terms coming on here. And we have the Hamilton-Jacobi-Bellman equation for the firm too. So we have two value functions. This is the Hamiltonian. This is the sigma term. The Hamiltonian basically means the integrand of the objective function, and then the dynamics. But the dynamics is multiplied by lambda 1 in the Hamiltonian, but lambda 1 is nothing but the first derivative of the value function for the firm 1. Similarly, the lambda 2, which is v sub x2, is the second, so the derivative of the second value function. And then we have a diffusion term, which gives you, as we talked about it, the diffusion term brings in the second order term from the value function. Because when we look at the Brownian motion, remember we did the Taylor series expansion, and the Taylor series expansion, we had to carry one more term because the Brownian motion is very large swings. So even the square root, even the square of that is still, the second term is still significant. And so we keep that. But what Sethi model did in 1983 was to show that I can find a linear value function which will satisfy all these equations. And if I do that, then this term doesn't matter. Because if I have a linear value function, then this will disappear, this will disappear. You see my mouse, by the way? Do you see my mouse?
Yes, we do.
Okay, good. And if that one disappear, then the solution is kind of similar to what we did in chapter 12. It's still a stochastic problem, but all I'm saying is that by doing some tweaking of the model, I was able to remove this and able to solve the problem closed form. And so then we take the derivative with respect to u1, and that will give you 2u1 and give you nothing. And so we will have there's a 2 sitting here. So we get a u1 star and u2 star x in terms of the value function. So once we have the value function, these will be defined. So basically, what we're going to do is we're going to substitute these guys into these equations, and then we remove the max. When we do that, we will have two coupled HJB equations given like this. So we substituted the optimal values, and now we have a messy looking equation, which you can see there's a multiplier of these, there's a double derivative. So in general, these problems are not easy to solve. But we have been able to show that as long as you can find the solution of these, which satisfy in the finite horizon, satisfy the terminal condition, in the infinite horizon, satisfy some growth condition, then you have an equilibrium. We cannot say that that's the only equilibrium, because there may be another solution to this than the one that I propose, and there may be another equilibrium. But as of now, we do not know there's another equilibrium. As of now, we don't know there's another solution. And if there is one, we don't know how to solve it. And my own hunch is that this is the only equilibrium. But that's how that is. We cannot say there's a hunch, and that's about it. Notice now, V1 is the value function of firm 1. So it's going to increase with its market share. But V2 is the value from the second firm, and its market share is 1 minus x. So we're going to write this as 1 minus x here. So that's something you need to worry about. It's not, if you took beta 2x, it'll still be okay, but then beta 2 will become negative. So you can still do beta 2, but it'll be a different beta 2. Okay. but this is more symmetric. And then we do the same thing. We substitute, we take the derivatives of these will become 0. We take the derivative of these v sub x1, v sub x2, so we substitute them back in there. And when substituted back in there, we equate the different terms to 0. Coefficients of x and coefficient of constant, we 0. And then what we do get is we get 4 algebraic equations. We have 4 parameters to define these functions. And if we can solve for alpha 1, beta 1, alpha 2, beta 2, we will have solved these equations. And to solve alpha 1, beta 1, alpha 2, beta 2, we should solve these algebraic equations. Now, the algebraic equations are not easy to solve many times. Okay? But here we are able to solve these equations. And what we will do is we eliminate variables. And when we came, so rather than do it, let me see what I'm doing now here. We will first consider the special case of symmetric firms. That is pi 1 equal to pi is equal to pi 1 equal to pi 2, c equal to c1 equal to r, r1, r2, or so all of these are symmetric. If they are symmetric, then we know alpha will be alpha 1 and alpha 2, and beta will be equal to beta 1, beta 2. That means we have reduced the problem of 4 parameters to only 2 parameters. So we can substitute for beta 1 and beta 2 beta, rho 1, rho 2, rho, and so on, and we get 2 equations in 2 parameters. And then so these 2 equations are these equations. And you can see that one of these equations is quadratic. The other one is also quadratic. So if we solve any of these 2 equations, we will get 2 solutions for beta. That's easy to solve. One is, in this case, we can show that one is negative, which doesn't make sense because beta should be positive. If you look at it, beta and beta 2 both should be positive, which means beta should be positive. And so we take the positive root, and then once we substitute the positive root back, we can get the value of alpha. That's the solution procedure, okay? So first we solve for beta 2 values, we take the positive values, then we put the positive values back in there, and we get the values of alpha. When we do all that, we get the following solution, where R is R squared by 4C, W is rho plus 2 delta, and we're going to change W to D, I suppose. And so once the alpha and beta are solved, then the value functions, these value functions are defined, these are defined. And once these are defined, we can see the control. This will be just beta 1, and this will be just beta 2 or minus beta 2 in this case. And so we will get the solution of control, which is given by beta, and u2 is given by beta r square root of x divided by 2c.
Professor,
Yes.
I have a question. Solving, I'm not sure whether this one was the case or not, but after doing all these algebraic equations and finding a solution to the optimal control, we have to put it back to the differential equation for the state. But I wasn't able to figure out how to integrate that equation in order to find.
No. Once you have these, you put that in the differential equations here, right?
Yes.
Then you get these equations. So
Yes.
all you now to do is to solve these equations. You don't have to go back to these anymore.
Oh.
That's not necessary anymore. You're done.
Oh, so we have to find the alphas and betas.
Right. We're going to find alphas and betas because we are proposing that the solution of these 2 equations will take this form.
Okay, yeah.
So we are actually going and saying obviously if that solution doesn't satisfy, then we have to go somewhere else, right? We have to figure out how to solve this system. And
Uh-huh.
maybe we cannot solve this system closed form, then we have to solve it numerically, right?
Yep. Yeah,
But that is
yes.
complicated because um, um, yeah. So we have not um, tried numerical solutions. Maybe one day, if I have time and I find somebody who's good in doing numerical solution of differential equations, then maybe I'll look at that. But we only get one equilibrium, and if it's unique, we're good. If not unique, then all we can say is we get one equilibrium, right?
Yes.
This a Nash equilibrium. So all we have to do is solve these. These are algebraic equations. These are not differential equations. So I'm taking the symmetric case. When I take the symmetric case, then alpha equal to alpha 2, beta 1 equal to beta 2. So I can call them without the subscript, right?
Yes.
So I have
Yes.
alpha and beta, and these equations reduce. Remember, this equation are similar, right? So we only need these first two equations. We don't need
Yeah.
these. So these two equations, I just put beta 1 equal to beta and alpha 1 equal to alpha and rho equal to rho. So I get this. So now you see
Yes.
this is beta square plus beta delta minus rho alpha equal to 0, right?
Yes.
That's a quadratic equation which you can solve in closed form for beta, right? Minus b plus
Yes.
minus
Yes.
e square minus
Yes.
4ac divided by 2a. We all know that formula from God knows when. We learned that. But when we have that, then we can actually, in this case, it's very easy because there's a square root and there's something outside, and we can easily show whether one is positive, one is negative. We know which one is positive, which one is negative. Okay, and we
Yes.
also have assumptions that we have already. In our case, we also can show that there is no imaginary solution here. Okay,
Yes. Yeah.
so this is positive, so there is no imaginary solution, and so then we substitute the value of beta, the positive value of beta back in here, okay? And,
Yes. To
and then we
find
get
value.
alpha. Then we get alpha, right?
Yes. Yes.
So we get the beta and alpha. And these are long formulas, so I compress them by calling R to be R squared 4C instead of writing R squared 4C here. W0 plus delta. You can put them back and remove R and W if you want to, but that's what I did. And now I have the value function, right? You just plug alpha and
Yes.
beta back in here, and we got the value function.
And that's it.
That's that. And then with the value function, we get the control, right? Our
Yes.
control formula is right here, right? V sub
Yes.
x1, which is beta 1, this is beta 2, right?
Yes.
We plug that back in, is beta 2. Uh, and so we plug that back in. And remember, Vx2 is minus. Remember, Vx2, V sub x2 is minus because of this. Remember, sorry. Remember, V sub x2 is because there's 1 minus x, right? So V sub x2 is
Yes.
minus.
Yes.
But because it is minus,
The minus will cancel out. Is that
minus
what
will
you're
cancel
saying?
out. Minus will cancel out. So we will have these equations, and we will have a solution which is symmetric.
Yes.
As you can see, this is symmetric.
Yes. Yes.
I
The
am
market
increasing,
are
right? I'm increasing my advertising if the population that is not buying is increasing, right? My product, because there's a lot of market going to the other guy. So I'm going to try to increase my advertising to persuade these guys to come back to me. Likewise, this
oh,
guy does the same thing, right?
yes.
He's
Yes.
trying to he's trying to steal from me, and I'm trying to steal from him. That's Nash equilibrium in this case.
Okay.
Now we go to the asymmetric case. Asymmetric case, we have four parameters, right?
Yes.
So we have to solve these equations simultaneously. And the way
Okay.
I've done it here is that I keep substituting for beta until I get an equation in beta which is power 4. Okay,
Okay, yeah.
so it's in beta 1, but it's power 4. It's beta 1 4, beta 1 cube, beta 1 square, beta and constant and 0, right?
Yes, so it has four roots.
It's got four roots. It's called a quartic equation or also called a biquadratic equation. And because of four roots, we need to figure out, and we, in Prasad and Sethi paper, we show, and that requires a little bit of algebraic knowledge of roots, how to solve these equations. We can show that only one root is positive. And we take that positive root. The problem is that if you look at the Mathematica and the formulas for beta 1, right? The formulas of beta 1 is complicated, right? There are,
Yes.
and if you look at those formulas, you can say root 1, root 2, root 3, root 4, right?
Yes.
You cannot say always that the root second is the positive root. You cannot say that. Depending on the
Yeah.
parameter, one of the root will become positive. We prove that one of the root will be positive. We cannot tell you right away whether it's the first one, the second one, the third one, the fourth one. The Mathematica gives you a formula for four roots. MATLAB gives you formula for four roots. These are closed form formulas. Up to four equations, we can solve closed form formulas. And so we can call them root 1, root 2, root 3, root 4. You can number whichever way you want it. But once you number them, you cannot say root 1 is going to be always positive. The root 1 may become positive for some parameters. The parameters, some pi 1, pi 2. The root 2 may become positive for other values of pi 1, pi 2. You understand what I'm saying?
Yes.
But at this point, the paper does all of that stuff. It tells you which of the roots are positive. I'm not doing that here. What I'm doing instead is going to do the numerical. And once you take the numerical, you can find out which root is positive, right? Because you have numbers, right?
Yes.
So that's,
Yes. Yes.
yeah. So I have beta 1. Then in terms of beta 1, whichever is the positive root, you put that one here. You get alpha 1. And whichever is
Yes.
the positive you put here, you get beta 2. And whichever is positive here, you can put here and you get alpha 2. So you go sequentially. Once you have the positive beta, when you put it in there, you get alpha 1. And then we have
Yes.
positive beta, when you put it here, you get beta 2. And then once you have
Yes.
beta 1 and beta 2, you put here and you get alpha 2. So we get all.
Yes.
So you start with the positive one and you get all others. And as before, I don't know how to remove this bar. Um, I have no idea. Uh, but anyway, and R1 is R1 squared by 4C1, R2 is R2 squared by 4C2. And this is very similar to this definition of R and W here. Okay, but now we have R1 and W1 and R2 and W2. Okay,
Okay.
so now once we solve this problem, we can say something about what is going on. One of the important thing that we can say about is this. We have this number called Ri, which is Ri squared divided by 4Ci. Now, what's going on here is, suppose the firm I, if if R1 is bigger than R2, then R1 is more efficient, right? Because its advertising is much better, it's a more persuasive. Maybe it has better models than the other one. Okay, but if it has better models, they're sitting trying to sell a car, and hopefully that works, then chances are you have to pay them more, right? So it's possible that a firm R1 is effective, but the cost of that advertising effort is not low. So what I'm trying to say is, if R1 is high and C1 is low, then we know that firm is more efficient, right? Because it's more efficient in effectiveness and is also more effectiveness in, more efficient in cost. But life is not so simple. In life, usually R1 is high, then C1 will also be high. because you have to pay more to get better people who are more better advertisers. Okay, not as bad as me. I have a YouTube channel, but somehow I see other people have millions and millions of subscribers, and I have now gotten to like 288 subscribers. Can you believe that? So, uh, so this factor Ri tells you how effective you are, how efficient you are. So, if you give me R1 and if you give me C1, I can compute R1, big R1. And I also compute R2. And I can tell you if R2 is bigger than R1, then R2 is more efficient. So this is the measure of efficiency. That one we can only tell using the model, right? It gives you the efficiency. So 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 whatever R1 and R2, whatever R1, R2, C1, C2 is, or R, we can measure this, and this gives a measure of the power of the firm I. And now we can see, let's give an example. We're going to assume discount rate to be 5% for both of them. We're going to assume margin is the same for both of them. We are assuming, we are assuming delta is same for both of them. But we will assume that the R1 and a C1 are such that R1 equal to 1 and R2 equal to 4. Remember, we don't need, if you look at the model here, we never need for our solution for the time being. See, everything is defined in terms of R and W. You see that? So we don't need small r and small c anymore. Small r and c act like together like this. You don't need to know them separately. As long as you know this, you're done in this model. This is simplifies the model. So I only need to know what is capital R1, capital R2. However, how you get to this one with any combination of small r and small c, it doesn't really matter. All you need is this number. And we have R2 to be this and sigma x to be this. And for this, we start. Remember, we begin at the 50% share of the market. Each company, this is the share of the first firm, 1 minus 0.5, which is the 0.5 is the share of the other firm. So we begin at 0.5, 0.5 for both firms. But R2 is more efficient. So over time, you can see what is going on. Over time, R2 is increasing its market share. And because they share the market, 1 minus of this is this number on this side. So this is x, this is 1 minus x. You can see that over time, the sample path of the market share is this because the Brownian motion fluctuates. And we can also show that the average path of the market share is given by the dotted line. And you can sort of see that over time, on average, R2 will eventually in equilibrium, long run equilibrium. I mean, this is an equilibrium. This is an equilibrium solution. But now I'm talking about the long run equilibrium in the sense of Kenneth Arrow that we did in chapter 2 and 3, where we define what is called the long run stationary equilibrium for a single player control problem. We can see that in the long run, expected value of the market share of the second firm will get to 0.8, approximately 0.8. And this guy will go to 0.2. So you can see the market power. So that can be defined as a market power. Ri could be defined to be the market power of the firm firm I. We use Mathematica, by the way, to do all this. Let me just say something here. This is one of the sample paths. If you run another Mathematica thing, you will still get the dotted line, but you will get another sample path. every time you do something, you'll get another sample path because that depends on the random number you generate, and it will give you a different sample paths. Okay, so that's number one. Number two, because my control is given by these formulas, and I am feedback control, so I have to put the observed value of x here, and then I will apply that control. So you can see the observed value of the x is the observed value of x being a stochastic process means that the u1 is also a stochastic process. So what I'm actually reacting to. So if I'm here, I'm going to react to this share, and I will try to advertise more to capture because I lost some of the market share, and I will try to advertise more to get up. But my control is not going to be based on the expected value. My control is going to be based on the observed value. And the observed value is a random process, so the control will be a random process. Now, if I remove sigma, if I remove the sigma from this problem, you will see that the value function will still be the same, because that was what Sethi model tried to accomplish. Because that was the price I have to pay for tractability in this case, or closed form solution in this case. So if you remove sigma, then you can see that your path will be exactly the dotted line, and your control will be given according to the dotted line. It will also be a non-random. But because of the sigma, the process is not random, the control is non-random, so I still have a stochastic problem, even though its value function. Remember, value function is always the expected value. Remember the value function? Yeah. So value function is defined to be expected value here. You see that? And once we do the AJB equation, what we get, this value function, is the expected value given a beginning value of x. This is the expected profit from here to infinity, present value, expected value. So that expected value will be the same for the dotted line, because dotted line is not expected anymore, it is the value. But expected value of this stochastic process will be the same as the value of the dotted line. But the sample paths are not going to be the same. One more thing I want to mention is that Brownian motion can go anywhere. But we have shown in our model that stochastic process x will remain bounded between 0 and 1. It will remain bounded between 0 and 1. So that sample path will never cross 0. It will not go below 0. And it will not go above 1. But you know what? It can be below this sample path. This sample path could go all the way up to here. And that one then will go above it. That's possible. Yeah, we did not put that, but the probability of that happening is very low. So what I'm trying to say is that Brownian motion will hover around this expected value path. It will vary from this, but higher the variation, lower its probability. That's what I mean by that. However, infinity is another object. It's a very complicated thing. So if you take the infinite horizon, almost certainly this path will go all the way here, all the way there, close to 1, all the way close to 0, from time to time. Not very often, but from time to time. Now, not very often, but infinitely often. And another language of mathematics. That means even though Suppose I draw a line here. I draw a line here. Suppose I draw a line at 0.6. I can tell you that that path will go below 0.6 infinitely many times over the infinite horizon. But it will go not frequently. That means it will go below 0.6 maybe now, and then maybe 20 years from now it'll go again below 0.6, and maybe again 30 years from now it can again go about 0.6. But because infinity has got infinitely many years, it will go below that point infinitely often, but not so frequently. If I draw a line at 0.1, that path will go below 0.1 also infinitely often, but not so often, so frequently. And lower the line I draw, lower the frequency. So if I draw a line at 0.01, maybe the expected value between two crossing of that line, maybe 3,000 years. Who knows? It depends on the data. But I'm trying to give you a sense that it will cross 0.01, but maybe once in every 3,000 years on average. That's the kind of thing what I'm talking about. Okay. So that's all conceptual understanding of Brownian motion, and it's a technical mumbo jumbo, but it is true. Any question? So we just talked about firm being more powerful, and then that was the status in 2004, and then we were three of us were sitting in Prasad's office, and we said, okay, we did this to Nash. Sorger already did it before us. How about Steckelberg? And one of the person was doing static model of cooperative advertising, and we started thinking, why not do cooperative advertising in continuous time and see if we can do a Steckelberg game? Oh, yeah. So this is a summary. Let me just do the summary here before I go to the next one. The preceding section, they have dealt with the differential game in which all players make the decision simultaneously. We now discuss different game in which two players make their decision in a hierarchical manner. That would be the next thing that we're going to do, which is the Steckelberg game. This is the Steckelberg. Player having the right to move first is called the leader, and the other player is called the follower. We know this is Steckelberg is also called leader-follower game. If there are two or more leaders, so what I'm trying to now say is that suppose there are two leaders, two manufacturers, one retailer, for example. Then the two leaders between themselves will play. You cannot see me, right? In this, when I do the slice here, you cannot see me, right? Do
We
you
see you
guys
on
see
the
me?
side.
Huh?
We see you on the side.
Oh, you do? Oh, I did
Yes.
not know that. I don't see you. I want to do something like that. Let me see. How do you do that? It's a view thing, right? How do you do that?
I think if you present full screen, you cannot see yourself. It happens to me all the time.
Okay. But what about, okay. But you can see me even if I'm on full screen, right?
Yes.
Okay. Okay. So when I do my hands like this, you see me, right? Because I don't see
Yes.
myself. Okay. Fine. Let me stay with the full screen then. Okay. So what I'm trying to say is if there are two leaders, then the leader will play Nash game. If there are two followers or more followers, they will play Nash game. But between leader and the follower, there will be a Steckelberg game. Okay, I will say a little bit more about it. We have time. We can spend as little time for the other things as we have. Okay. Again, we have open loop and closed loop solution, but I'm interested in feedback Steckelberg. In open loop, I will announce the whole strategy as a leader for the entire time, and the follower will react to that and find his or her strategy for the entire time. That is a very difficult situation to solve, but I mean, not it's a difficult situation to fathom in practice because um, um, it's not it's not it's like my current decision are also is based on the leader's decision in the future, because the open loop, by the way, is mathematically a dynamic problem. Now, practical is a dynamic problem, but mathematically it's a single period problem. Everything is decided at time zero and the game is done. So there's no big dynamics coming into play in terms of decision making. But once you decide, there's a dynamics going on because the world evolves according to the differential equation, but you already made your decision. So you're out of it. Okay. So open loop solutions are not time consistent in the sense that if I solve the problem now and give you the solution for the entire horizon, and then it's a stochastic problem, and then if I go to a year later and I resolve the problem with now our initial conditions are different, I resolve the problem, I will not get the same strategy for the remaining horizon as I did when I solved that problem at time zero. So that means if I solve the problem at any given time after zero, then I may get a new solution. And if I get a new solution, then as a leader, I benefit from the new solution. So I will tell the follower, by the way, I told you that solution at time zero, but I changed my mind. And what are you going to do? He changes his mind. And so one way to justify an open loop is to have an assumption of credibility. That means the person who leads cannot simply change the decision once she committed to a decision at time zero. So in economics, it's called full commitment games. The problem is, how do you get a full commitment? In all matters of life, we have seen that sometimes these full commitments are not possible because if the leader gains by changing the decision that he already announced, because it's beneficial for him to change, then he may change. So the only way to discourage the change is to take him to court. There has to be some penalty of, I mean, there's a gentleman's agreement, but the gentleman's agreement don't always work. Okay. Uh, there was a gentleman's agreement that the Ukraine will be left alone, and Mr. Putin went to Ukraine anyway. And so in politics and in economics, it is a possibility that if somebody gains by doing something, then somebody is going to not stick to the gentleman's agreement. Some people may, some people may not. And so in some sense, the open loop have lots of flaws of this kind. And even if the court penalty is there's another problem. Suppose the penalty is upper bound by $1 million, but changing your decision saves you $2 million, then you're going to change. If you don't feel remorse, if not everybody feels remorse, right? So all I'm trying to say is that there are many ways to look at it. So I am proposing feedback, Steckelberg, And we went through the literature. Um, there is some work done in the literature on feedback Stackelberg, but it is difficult it is old, it's difficult to follow, and we have to rewrite some of that, and we have to develop some new results in order to continue this. And that paper is given in this one and the 2019 paper. So we have two papers on feedback Stackelberg. This is on many different kind of equilibria, and this is on feedback Stackelberg, the 2019 paper. Uh, Both are in the top journal in control theory called Siam Journal of Control. And that's where we develop some theory that allows you to say, like in the last slide I said, if I can get the value function, then that's an equilibrium. That requires a proof. And that proof is in this paper, 2019 paper. Okay? Now, let me say a little bit more about it. In our field, we talk about what is called a news vendor problem. And we talk about a supply chain which has a news vendor. Okay? And we talk about the manufacturer setting a wholesale price and the news vendor ordering order quantity. And we form that as a Stackelberg game, single period Stackelberg game. If you form that as a single period Stackelberg game, and then we show that there is something called a double marginalization. You listen to some of these papers, even though you may not have taken a course on it. And that means there is inefficiency of behaving in a decentralized fashion in a supply chain. And then we try to create a coordinating contract. Some of these contracts called revenue sharing contract, some called buyback contract, and there are a number of different kinds of contracts that allows you to coordinate the supply chain, which means that under the contract, supply chain will give you the result as if it was a centralized integrated channel. That's called a coordination. So most of the literature in supply chain in operations management is a single period. And we thought that the people did not do two period or multi-period because it was technically more difficult. They did not get close form solutions. And more when I started working on dynamic Stackelberg games, I realized that part of the reason they did not go into is because they did not know. They did not know the theory of Stackelberg, dynamic Stackelberg. And they never attempted to solve it because they did not know the theory. And then we wrote a paper with one of my doctoral student, Tao Li, who is now a tenured professor at UC Santa Clara. And we published that paper in POM in 2009, I believe. This one, Hey Prasad Sethi. And there we show a two-period Stackelberg game. And we show that if you do open loop, you have those problems. So we don't want to do open loop. But we do feedback. Now, here's a little issue that you want to talk about, or you want to learn about. It's not, generally speaking, people don't know all of these things. But in a single period problem, we call the leader who is a first mover, he or she gets a first mover advantage. It's called a first mover advantage. But if you have two period problem, then we cannot guarantee the leader has a first mover advantage. We can guarantee the leader has a first mover advantage in period one and has a first mover advantage in period two. But it doesn't have a global first mover advantage. Okay? And so that is a situation which people will say, okay, so the leader doesn't have a first mover advantage, so maybe it's not a good thing, whatever. But we can coordinate. We found in this paper that we can find a coordinating contract. If you have a coordinating contract, then the whole supply chain in two period gets integrated, and nobody loses anything. So what I'm trying to say is that we can do feedback Steckelberg, and we can find a coordinating contract which gives you the centralized solution, then we are done. We have no problem anymore. So that's what I was pushing. And now I'm working on continuous time, not just two period. And we do have some coordinating contracts in continuous time, um, not revenue sharing, not buyback, but some other contracts which are coordinating. We have a we oh no, this is not a paper. This is this is the paper where we do the continuous time, Steckelberg. The paper that I talked to you about, two period, is with Tao Li and Jun Zhang, who was a professor here. So it's a Li Seti Zhang paper, and that's also in POM, but that's two period problem. Control theory does more than two period. It does infinite horizon or finite horizon. So we did that. Okay. So with that kind of introduction, um, we continue. So now we have a manufacturer who sells a product through a retailer. And the retailer has a fraction of the potential market. So now we have only one retailer, no competing retailer, and the total market is size 1, and the retailer captures the market size X, where X is between 0 and 1. So the idea is to advertise to capture more and more of the remaining market that is not yet captured. Okay? And in order for that, you retailer would advertise. And if the retailer advertises, then he can capture more market share. But it turns out that in decentralized setting, the retailer may not advertise enough. And if it doesn't advertise enough, then there is not enough sales. If there's not enough sales, then the manufacturer also loses. So what manufacturer does is to tell the retailer, I will subsidize your advertising to a certain percentage. So WT is the percentage between 0 and 1. That will be the subsidy rate. So if I say subsidy rate is 0.2, then I will pay the 20% of the advertising expenditure of the retailer. By doing that, I'm trying to encourage the retailer to advertise more. And when retailer advertises more, it benefits the supply chain. And he also gets benefit. And so you see, subsidy rate is going towards coordination. Okay? You can call it a subsidy contract, but it may not be 100% coordination. By doing subsidy, you may have to use another tool to supplement your subsidy rate. So you may have to have a slightly more complex contract to get full coordination. But even if you don't get a full coordination, the whole literature on cooperative advertising, called co-op advertising or cooperative advertising, is that the manufacturer gives a support to retailer, and that literature is a lot. There's a lot of marketing literature, mostly single period, that tells you that the cooperative advertising is a huge um, uh, phenomena in the sense, and the number of dollars that goes into cooperative advertising could be as much as $50 billion. It was $27 billion 10 years ago. So those data are available in the papers that we have written. We talk about those things, but I'm not doing that here. So we are now doing a cooperative advertising, and we're saying that the manufacturer will do the cooperative advertising and the retailer will do advertising. So the cost of advertising is quadratic, so it'll be UT squared. So if the control is UT, advertising is UT, then the cost is UT squared. If the subsidy rate is WT, then the retailer's advertising expenditure rate is 1 minus WT UT squared, because the WT is paid by the manufacturer. So the manufacturer also incurs advertising expenditure even though he doesn't advertise because he's providing the subsidy. So his cost is W2 UT squared. So now we have a model. We have a model in which this is exactly Sethi model of 1983. No difference. But the cost function, because Sethi model there was only one player and there was only one cost function, and that cost function was without this term. Now we have two cost functions. One has 1 minus WT term, one has a WT term. This is retailer, this is manufacturer. This is a leader, this is a follower. So now we have a Steckelberg game. The retailer manufacturer will announce the subsidy rate. Then the retailer will react to that subsidy rate and announce advertising expenditure. And the manufacturer will know the response function and obtain the optimal subsidy rate. And once she obtains the optimal subsidy rate, the retailer will know exactly how much to advertise. Okay, once again, in a single period news vendor, here's how the game proceeds. The manufacturer gives the wholesale price. Retailer gives you a function of ordering quantity. Ordered quantity says the following. If you give me this wholesale price, I will order this much. If you give me little less wholesale price, then I will order more. So the ordering function is coming out of optimization by the retailer given the wholesale price. So the single period problem gets solved like this. So you get the wholesale price. The retailer will give you a function Q of W, where Q is the quantity and W is the wholesale price. QW is a function of the wholesale price, which the retailer will come up with. And both people can solve mathematics. So the manufacturer will use the Q of W in his cost function, and he will optimize over W. So that will give you W star, the optimal subsidy rate. And once you get the optimal subsidy rate, then the Q of W star will be the advertising because Q of W has already been obtained. So that's what we mean by a backward solution of the game. Okay, the solution moves forward. You announce W and he announces advertising. That is how the sequence is. But the way you solve it is backward. You first find out the reaction function for any given W, then you use the reaction function to find the W, and once you find the W, you implement it forward. Okay, so that's make that distinction, because in a single period it is simple to see, but in continuous time and a multi-period game, each period you have to play a Steckelberg game. Remember, we are not doing open loop. We are not doing the entire wholesale price over time or entire cooperative rate, subsidy rate over time, and then the person will react to this entire function. We're not doing that. We're playing a Steckelberg game in each period according to a certain rule. And in continuous time, we are playing the Steckelberg game at each instant, according to, again, the certain rule. And you can think of the instantaneous continuous time game to be a limit of a multi-period game where each period becomes shorter and shorter, and in a limit, you get a continuous time solution. So you can think it that way. That's what Bassar and Olster do in his book, on their book. It's a famous book, and he's also a co-author of mine in some of the papers. Bassar is not Olster. Um, Olster and Bassar were control theorists. Bassar is more of a, both of them are game theorists, and they wrote a book called non-cooperative game theory. And that book was written actually earlier than this, but this is the newer edition of the book. It's got Siam Classic kind of book. Bassar is a professor at Urbana-Champaign, very well-known guy. Olster is a well-known guy in Amsterdam, in Netherlands. I know both of these guys. Olster wrote a control theory paper way back when, and the two Chinese people descended in Amsterdam to have a dinner with him. He did not know what the dinner was about, but anyway, they discussed his paper, and these Chinese people go back to China, and his paper became the justification of the single child policy in China. For those you don't know, just Google Ulster and you will find the paper that actually these two Chinese people, I don't know their names, but maybe in Wikipedia or in Google you can find his name. And then they went back, and that became a justification of the single child policy, which you all know pros and cons of. But talking to Ulster, he says that if he had known that they justified that policy based on his paper, he would have never gone to dinner with these guys. But that's the history. It's an old history. I just tell you about it. Okay. So now we are going to describe how we play this game and how we solve this game. Okay. So first we have the Steckelberg problem. We have a dynamics and we have the objective function. Now let's see what we do. We assume that this is full observation game, no asymmetric information. That gives you another economic theory called mechanism design. Okay, we are not going there. Although I did some of it in chapter 11, and those who want to do continuous time mechanism design would benefit from that, because it was quite a bit of effort to look at all these economics books to write that chapter, because most of those papers don't do a good job because they assume too much for people to know, because they are writing papers in a journal, and so they're not suited for a textbook. So I had to do a lot of explaining and make it a control theory, whatever. Okay. So at each time, both players know the current system state, which is market share, and follower knows the action of the leader. So what I'm trying to say here is the following. The follower, which is the retailer here, knows the subsidy rate at that time t, because the subsidy rate is announced by it is decided by the leader first at each instant, and the other guy follows it by deciding how much to advertise. Notice, so his advertising depends on the subsidy rate at time t. Okay, but the manufacturer decides the subsidy rate based on the system state and the reaction function of the other guy. The system state is observed at each time t, so the manufacturer has a feedback function. W is a feedback on the system state x, W of x. But the follower is not reacting to W of X. Follower is not reacting to the function W of X. He's reacting to the dollar value or the subsidy rate obtained by the manufacturer or the leader using his feedback policy at that time t. So what the follower is reacting to is the number subsidy rate, 0.2, 0.3, 0.5, and not the function W of X, which will also give you 0.2 at that point in time. But he's not reacting to that in the sense that his advertising policy at that time t does not depend on that function. That means his advertising policy is not a function of a function. It is just a function of the subsidy rate obtained by the leader at that time using whatever method he was using. Let's put it that way. So this idea of knowing mathematics by both guys doesn't work because retailer knows his feedback function, but he's not taking that into account. Because if he takes into account, it's no longer a feedback Steckelberg. It is another game which is very difficult to solve. And it's not time consistent either. So a lot of things need to be known and they're kind of subtle. So here's the rule of the game. First, the manufacturer owns the market share and selects the subsidy rate, which is based on market share. But he knows that function. So does this guy. But he acts on that function. Then the retailer observes that part. That's it. He observes only what the subsidy rate was. Although he knows the market share, his function UT will depend only on WT and XT and not on the function of W of X. Okay. The system evolves over time, and this played in continuous time at t equal to 0. And then one can visualize this game as being played at time 0, delta t, 2 delta t, and then let delta t go to 0. So that's what's going on. Now, how to solve this problem? We're interested in deriving an equilibrium menu, Wx. Wx is the menu by which manufacturer will decide his subsidy rate. That's the function that he has to come up with. Follower, on the other hand, has to define U, which is the advertising effort, that depends on X, just like this guy, but it also depends on W. Remember, I did not write W dot. I did not write the function. You can write W of X, but that X is to be observed at that time X. But I don't want to confuse because if you put W of X here, some people think it's a function. But when I put W of X here, it means W of W obtained at that X, not as a function. Okay, so I don't write that as a function. I just write it as a W. By the way, it is so subtle that if you read my 2009 paper, this description there is not correct. We did not, we knew in mind what we were doing, but when we wrote something for the general audience, we tried to simplify it and we made mistake. We didn't correct it because we have corrected that in other papers. And so it was not necessary to write an errata. But that's what is going on. It requires quite a bit of notation to get there. And we were not willing to do that in a POM paper. And we didn't think much at that time either. Okay. I don't write papers with mistakes, but sometimes there are things. And I would say that description, the paper is not wrong. That description of how you do the policy is not precise. You can interpret in the right way if you want to, but you can also interpret in the wrong way if you want to. Okay. See, that's the notation you need. And I will take a break in a few minutes, but let me continue at least the policy and then we'll go to the equations afterwards. So in order to specify the strategy, I need to specify some spaces. So this is a script W. Script W is a set of functions W. These functions take the market share that is between 0 and 1, take the market share between 0 and 1 and brings it to the subsidy rate between 0 and 1. So this is a set of functions of market share mapping into subsidy rate. Okay, and we need some regularity. That means we need some continuity, and we need a little bit more than continuity. We need ellipsis continuity, and that is needed for us to have a solution of the differential equation. Okay, that's basically what it means, and we don't get any more than that right now. Then we define another set of functions, U, which is the function advertising rate, and is a function of X and subsidy rate. And it brings you to advertising rate, which is positive or non-negative. Notice now, this is a function of X and a function of W, not function of an element in this. It's a function of that W, which is coming here. That number, which is the result of this function, that result is coming here. Okay, so that is the function. Also, we assume this to be continuous and lift is continuous. Now, take one W from this, which is a function, and take one U from this. So for a pair of strategy, which is consists of two functions, one from here, one from there, that should be, oh, we did go here. We did talk about this. This is supposed to be an epsilon, and not epsilon, but
Belongs to.
Yeah, I think we did talk about that, but it's okay. I'm providing a lot more detail now. We did not make those kind of details last time because we didn't have the time. So for a pair of strategies which belong to this cross product of W cross U, let Ys be the solution of the following differential equation. This differential equation begins at time t, where market share is X. So it takes any arbitrary time and any arbitrary market share. That's what we mean by that. Take an arbitrary time t and arbitrary market share X, and then you solve this equation given W and U. Given W and U, you will get a solution which will be S bigger than equal to T. See, S bigger than equal to T. So for any time S, this U will be a function of Ys and Ws, because Ys is here and the Ws is here. And this is Ys, and this is beginning. So we can solve that equation. When you solve the equation, we will call the solution Ys that began at T, that began at the market share X, given W and U. So for any W and U, there will be this state developing from T all the way to infinity. Okay, for every S about T. You can see that depends on W and U. So for any WU, I have to define this. Once I define that, I can plug into the objective function. So here's my objective function. The objective function has these two strategies. Okay. And for retailer and for the manufacturer. And I need to define that because it's not so clear what that means. So I define it. I define this to be integral from T to infinity. I discount all the way to T. So this becomes S minus T, because remember, I'm discounting the value at S at time T. Pi margin. And now remember, the market share is Ys at S. And Ys is coming from this. And it depends on W and U. So that's why this W and U. Because once you're W and U, the problem only depends on the initial value. So the initial value is T and X. So the problem now depends on t and x and w and u. And how it depends? Well, the t means I'm taking integral from t to infinity. And x, because I found this ys, which depends on this x. So pi m times ys minus w of ys times u of ys and w of ys at that time s. So that's fine. It's not a function. It's just the value at ys and the quadratic square. Same for Echelon. So now I define the objective function for any feasible strategy. Notice that evaluated at any state C means this. That is the notation that means this at any state C or Y or X, whatever you call it. Then I'm done. Now I have a feasible strategy and I have a feasible objective value. A pair of strategies W star U star belonging to W cross U is a feedback stack equilibrium if at star it's bigger than for any other W which is in that script W, for any X and any T. So what am I saying here? I'm saying that I have an equilibrium. And if the leader deviates, if the leader goes from W star and goes to W, which is a deviation from equilibrium, if he goes equilibrium, remember the other guy doesn't change his response function. His response function is still U star. But in the U star, he has to put W instead of W star. Because now he decided W, so he's going to react to that W. And now we're saying that this is bigger than that for any W. That means if the leader changes his strategy, he loses. That's one inequality. If the leader changes strategy, whereas the follower continues to the optimal response, then the leader loses. Let's look at this. Now I have the equilibrium again, but now the follower is changing the response function from U star to U. But the leader doesn't change. Leader keeps his strategy at equilibrium. But the follower is changes response function, which is no longer equilibrium response, is any other response, any other in script U. And so now the U has to act on whatever the leader is playing, and the leader hasn't changed, so it'll be W star here. So what we are saying now, if the follower changes his response, he loses. Notice follower is not changing his advertising expenditure. He's not changing his action. He's changing his response through which he's going to change his action. That's very important because if I put U to be similar to W, that means if I had a U which was not a function of W, just a function of X, just like W, then this equation, this definition reduces to Nash equilibrium. Nash equilibrium says if one player deviates, he loses, the other player deviates, the other player loses. Deviation means deviation in action. But in Steckelberg, the deviation of the manufacturer is the deviation in action. But the deviation of the retailer is the deviation of the response function, not action. So the space of deviation has been defined. And once you define the space of deviation, the equilibrium is like a Nash equilibrium, but it's in a different space. And it is therefore called a Steckelberg equilibrium. So that is all that was needed in a palm paper. And that would require another page or two. And we did not do it. We tried to see if we can explain these things. We thought we were able to explain this without doing all of this, but obviously we made a mistake. So I'm trying to tell you the following. If you are in a very subtle mathematical problem that you're trying to deal with, if you don't have a proper notation, then you're likely to make a mistake. So the notation is required. And notation requires time to develop and it need to be precise. And that's what we did. And this is done for the first time in our papers, at least, in the Ben Sousa et al. 2019 paper. In other papers, people have not been so precise, and so their language has the same mistake as my 2009 paper in PALM. At this point, we're going to take a break, and then we'll go to the next level of the solution. Okay, so let's take 10 minutes break.